All right, welcome to the deep dive. Today we're plunging headfirst into, well, something that sounds like pure science fiction, doesn't it? Quantum computing. But the thing is, it's quickly shaping up to be our imminent reality. Forget what you thought you knew about computers, because the very foundation is sort of being rewritten right before our eyes. So our mission today, let's cut through the noise, the jargon, the hype. We want to give you the essential facts, maybe some surprising ones, and really help you grasp what this actually means for you. And we're talking big money here already, over $40 billion in global investment. It's huge.
It absolutely is a really seismic shift, like you said, and it
Yeah.
feels like a pivotal moment right now. You mentioned 2024. That was significant. That's when we saw quantum computers achieve something called below threshold error correction for the first time.
Okay, below threshold error correction. What does that signal, really?
Well, it signals a move, a transition from purely lab experiments, theoretical stuff, to something that could actually become a commercially viable technology. And the key thing to remember is this isn't just about making today's computers faster.
Right, not just speed.
No, it's about tackling problems that classical computers, well, they just can't solve, period. Think about things requiring just enormous exponential computational power, like really complex climate modeling or simulating new molecules for breakthrough medicines. And you see the ambition companies like IBM are aiming for, what, 200 logical qubits by 2028? That's a massive leap.
Okay, logical qubits. We'll have to unpack that later. But first, the fundamental question everyone asks. How does it actually work? For anyone needing a quick refresher, or maybe just trying to wrap their head around it, what is the basic difference? Classical bit versus quantum qubit. Let's start there.
Okay, yeah, the core distinction. It's how information is handled. Classical computers use bits. Simple. It's either a 0 or it's a 1. Definitive.
Binary. Yeah.
Exactly. Quantum computers, they use qubits. And well, magic, I suppose, is superposition. A qubit can be a 0 and a 1 at the exact same time, and actually kind of anything in between until you measure it.
Okay, both at once. That's already weird.
It is. And to give you a sense of scale, imagine a 300-qubit quantum computer. Theoretically, it could process more states simultaneously than there are atoms in the entire observable universe.
Wait, hang on. More states than atoms in the universe.
That's the power of 2 to the n, where n is the number of qubits. It scales unbelievably fast.
Wow. Okay. My brain just did a little flip there. That's yeah, that puts the quantum in quantum leap. All right. So superposition is wild enough, but then you hear about entanglement.
Yeah.
How does that make things even weirder and more powerful? What is that spooky action Einstein talked about?
Entanglement. Yes, that spooky action at a distance. It's maybe the most counterintuitive part. When qubits become entangled, they become linked, deeply correlated. These correlations persist no matter how far apart they are physically.
So like miles apart.
Yeah.
Still linked.
Miles, potentially light years, it doesn't matter. They form a single, unified quantum system. If you measure the state of one entangled qubit, you instantly know the state of its partner or partners. Instantly.
Wow.
And it's this deep interconnectedness that lets quantum algorithms exploit probabilities in ways classical systems just can't touch. It's a huge source of the computational advantage.
Incredible. So you've got qubits in superposition. They're entangled. How do you actually use that? How do you make them calculate something useful? Is that where interference comes in?
Yeah.
Manipulating probabilities?
Precisely. Quantum interference is the tool we use. Think of the probabilities like waves. We can make them interfere constructively.
So they add up.
Right, amplifying the probability of getting the correct answer. And we can also make them interfere destructively.
Canceling each other out.
Exactly.
Right.
Diminishing the probability of incorrect answers. This quantum amplification is key. A really powerful example is Shor's algorithm.
Yes, the one everyone talks about with encryption.
That's the one. It can factor large numbers exponentially faster than any known classical algorithm. And that's why it's such a big deal. It poses a direct existential threat to current encryption standards, like RSA, which rely on factoring being incredibly hard.
Okay, so Shor's algorithm, breaking encryption. How worried should, the average person be right now? Is my online banking about to collapse tomorrow, or is this more of a future threat?
That's a crucial distinction. It's not an immediate threat today. Let me be clear on that. We don't yet have quantum computers large enough or stable enough, fault-tolerant enough to run Shor's algorithm on the huge numbers used in real-world encryption.
Okay, phew.
And this is but it's absolutely something we need to prepare for now. Think about data being harvested today. If it's encrypted with current methods, A future quantum computer could potentially decrypt it years down the line.
The harvest now, decrypt later problem.
Exactly. That's why developing and deploying post-quantum cryptography, or PQC, is so incredibly urgent. It's about future-proofing our security.
Fascinating. So if those are the core quantum concepts, how do we actually, program these things? You mentioned quantum gates and circuits earlier. Is that the nuts and bolts of it?
That's right. Quantum gates are the basic building blocks, the operations that manipulate the qubits. Think of them like the logic gates, AND, or not in your classical computer, but operating on quantum states.
Okay.
But they have special properties. They are unitary operations.
Unitary. Sounds technical.
It just means they're perfectly reversible, no information is lost. Unlike many classical gates, think of it like perfectly sculpting clay without losing a single particle. Common gates have names like poly-X that flips a qubit state, or the Hadamard gate, which puts a qubit into superposition.
Trace the 0 and 1 state.
Yes. And the CNOT gate, which is crucial for creating entanglement between two qubits. You combine these gates in sequences, forming quantum circuits, and these circuits implement the algorithms, like Shor's. It's been proven, theoretically, that certain sets of gates are universal.
Meaning they can build any possible quantum algorithm.
Exactly. That's what unlocks the potential to solve problems beyond classical reach.
Okay, so this leads to maybe the biggest misconception I hear. People ask, will quantum computers make my phone or laptop obsolete next year? Is there any truth to that, or is it just hype?
It's almost entirely hyped, frankly. A very common misconception, let's be really clear. Quantum computers are not universally faster.
Okay, that's important. Not faster for everything.
Definitely not. They excel at very specific, very hard types of problems, things involving simulating quantum systems themselves, complex optimization problems, certain mathematical structures, things classical computers really struggle with due to that exponential scaling issue.
But for everyday stuff.
For everyday tasks, word processing, browsing the web, checking email, simple calculations. Your phone, your laptop, they'll remain much, much more efficient and practical for the foreseeable future. Quantum computers also can't solve fundamentally unsolvable problems. They don't break logic. And a really big point, the one we touched on with error correction, they currently require extremely sophisticated methods to handle errors, which adds huge overhead in terms of the number of physical qubits needed.
That makes sense. And thinking about building them.
Mm.
It sounds incredibly complex. All that talk of extreme cold, manipulating single atoms. I guess there isn't just one single way to build a quantum computer, right?
You're absolutely right. It's a very diverse landscape right now, a real horse race between different physical approaches. The most prominent one, certainly in commercial development, uses superconducting qubits. That's the tech behind systems from Google, IBM, Rigetti.
And those are the ones needing the extreme cold.
Yes, exactly. Temperatures near absolute zero. We're talking 15 to 20 millikelvin, colder than outer space.
Wow.
But despite that challenge, they've achieved really impressive gate fidelities, getting close to that 99.9% mark. Then you have trapped ion systems. Companies like IonQ and Quantinuum are leaders here. They use individual atoms, ions trapped by electromagnetic fields.
How do they compare?
They offer much better coherence times, how long the quantum state lasts, seconds compared to microseconds for some superconducting qubits. And they also hit that high 99.9% fidelity. Then there's photonic quantum computing. Xanadu, Sequantum are big names. They use particles of light, photons, as qubits. A big advantage, they can operate at room temperature.
Well, that sounds much easier.
Well, yes and no. It's great for networking quantum computers together, but they face challenges with losing photons and detecting them efficiently. And finally, there are neutral atom systems from places like Quera, atom computing. They use lasers, optical tweezers to arrange neutral atoms in flexible arrays. Very reconfigurable.
But the downside?
Their gate operations tend to be a bit slower compared to superconducting or trapped ions, so different trade-offs for each approach.
Okay, so clearly these aren't just theories anymore. Companies are building real machines. What are some of the recent breakthroughs that really show this tech is moving out of the lab? You mentioned that error correction milestone.
Yes, that Google Willow processor result in late 2024 was huge, achieving below-threshold error correction. What that means, practically, is they showed that their logical qubits, these error-corrected groups of physical qubits, could hold quantum information more reliably for longer than the individual physical qubits making them up.
So the correction actually worked better than the raw components.
Exactly. They got logical error rates down to about 0.14% per cycle using 105 superconducting qubits. That's a critical proof of principle. You also see IBM pushing hard with their Condor processor, 11 121 physical qubits. That's sheer scale. And their roadmap is ambitious, targeting 200 logical qubits with their Starling processor by 2028 using a modular connectable design.
And how do we compare these different machines? Is there a standard measure?
Well, we're getting there. One benchmark that tries to capture both scale and quality is quantum volume. It measures the largest square quantum circuit a machine can run successfully. For instance, Quantinuum's H21 trapped ion system recently surpassed a quantum volume of 2 million. It gives us a way to track progress across different architectures.
Okay, so incredible progress, but you also mentioned huge hurdles. What are the really big roadblocks stopping these things from being everywhere? And when can we realistically expect them to make a difference? You hear such optimistic predictions, but also, some serious skepticism from big names in AI and computing.
Yeah, that tension is very real. The challenges are formidable. Error correction is still number one. That 99.5% fidelity we see now. It sounds good, but it's not good enough. Useful applications likely need 99.9%, maybe even 99.9% fidelity. That factor of 10 or 100 improvement is a massive engineering lift.
And you need tons of physical qubits for each logical one.
Right. With current codes like the surface code, the overhead is huge. Maybe 1,000 physical qubits for just one logical qubit. Very inefficient right now. Then there's scalability. Going from hundreds of qubits to the millions we'll likely need. The complexity of the control systems, the wiring, the cooling, keeping everything coherent, it explodes exponentially.
And new problems emerge.
Exactly. Things like correlated errors. Maybe a cosmic ray hits the chip, or qubits interfere with each other crosstalk. Those are much harder to fix than random isolated errors. Economically, the costs are just immense. Development, operation, those big cryogenic cooling systems need lots of power.
So it's hard to justify the investment.
It can be. It leads to that chicken and egg scenario. Who pays for the expensive hardware before the killer app is proven? And the final piece, which is critical, is the workforce shortage.
Not enough people who know how to do this stuff.
Precisely. Estimates suggest less than half the quantum computing jobs will be filled by 2025. In the US, maybe only one qualified candidate for every 3 open positions. Education systems just haven't caught up yet. It's a real bottleneck.
Wow. Okay. So given those massive hurdles, errors, scale, cost, people do, how do experts actually see the timeline playing out? When do we hit quantum advantage, where they genuinely outperform classical computers on useful problems?
Yeah.
You mentioned skepticism from people like Jan LeCun, Scott Aronson. What's the sort of realistic consensus, if there is one?
It's definitely a hot topic, and that skepticism is healthy. It keeps the field grounded. Generally, people talk about 3 phases. We're currently in the NISQ era, noisy intermediate scale quantum, roughly 2020 to maybe 2027.
Noisy meaning error-prone.
Exactly. Systems with maybe 100 to 1,000 physical qubits. Good for exploring algorithms, specialized optimization, some chemistry simulations, but limited by noise and scale. Next comes the early fault-tolerant era, let's say 2028 to 2035 perhaps. Here, we expect to see systems with maybe 100 to 1,000 logical qubits, properly error-corrected.
Ah, so that IBM 2028 target fits right in there.
Precisely. This is where we could start seeing real advantages in drug discovery, materials science, maybe complex financial modeling, and then further out the mature quantum era, maybe 2035 and beyond. We're talking 10,000 plus logical qubits, which means millions, maybe tens of millions, of physical qubits. That's when you could see truly transformative applications, radically new AI, high-fidelity climate models, breakthroughs in fundamental physics.
It's a long road.
It is. And those quantum winters, you hear about periods where investment cools off due to unmet expectations, like we saw a bit in 2022, 2023, are a real risk. The hype cycle is intense. Valid skepticism is important. The consensus is leaning towards broad quantum advantage, being maybe 10, perhaps 20 years away for many applications. It'll be gradual.
Okay, gradual unfolding. But putting aside the timelines for fault tolerance, where are we seeing value now? Even in this noisy NISQ era, are there tangible impacts? Real applications already happening?
Yes, absolutely. Even with today's limitations, we are seeing value. For example, using variational quantum algorithms. These often run in a hybrid mode, using both quantum and classical processors. They're being applied to things like simulating molecules for drug discovery or tackling optimization problems in logistics and finance, trying to find near-optimal solutions.
So useful, even if not perfectly accurate yet.
Exactly, finding good heuristics. Another area is quantum sensing. That's actually quite mature in some ways. Companies like Sandbox Sandbox AQ are already deploying quantum-based navigation systems that work where GPS doesn't.
Oh, interesting. Like underground or underwater?
Precisely. And the other huge area creating immediate demand, as we discussed, is post-quantum cryptography, PQC. Just the threat of future quantum computers is driving a whole market for developing and implementing quantum-safe encryption standards today. That's real value right now. And looking at specific industries, in financial services, you've got the big players, JP Morgan Chase, HSBC, Citigroup actively investing. They're looking at portfolio optimization, complex risk analysis, fraud detection. Early results show potential for maybe 2x to 10x improvements on certain problems.
And the bigger prize is faster simulations.
Right, those Monte Carlo simulations used for pricing derivatives or assessing risk could see quadratic speedups eventually. That's game-changing for finance. Even central banks are taking notice. In healthcare and drug discovery, the partnerships are significant. Google and Boehringer Ingelheim, Pasquale and Quibbit Pharmaceuticals, Johnson & Johnson.
What are they focused on?
Primarily molecular simulation, understanding protein folding, how potential drugs interact with targets in the body. The dream here is to dramatically shorten drug discovery timelines, maybe from 10, 15 years down to 5, 7 years, and cut costs hugely, from over $1 billion per drug to maybe under 500 million.
That would be revolutionary.
Absolutely. In logistics, that Volkswagen pilot project using a quantum approach for traffic routing, even with early hardware, they saw 15% shorter travel times, 10% fuel savings in tests, shows the potential even at small scale. And in material science, using quantum simulations to design entirely new materials from the atom up better superconductors, more efficient battery materials, novel catalysts for industry.
That's already a pretty amazing list of current and near-term applications. Okay, let's push the boat out a bit further now. What are some of the truly revolutionary applications? The ones still maybe on the horizon, perhaps a bit speculative, but scientifically plausible?
Right, the really transformative stuff. Well, one huge area is the intersection with artificial intelligence, a potential quantum AI revolution. Quantum machine learning algorithms promise, in theory, exponential advantages for certain types of pattern recognition and data analysis.
So AI that can handle vastly more complex data.
Potentially, yes. Quantum neural networks might process exponentially larger data sets, and things like quantum reinforcement learning could fundamentally change robotics and autonomous systems control. Then think about climate modeling and environmental solutions. Imagine processing real-time global atmospheric data for incredibly accurate weather forecasts or long-term climate projections.
That alone would be huge.
Immense. Or deploying networks of ultra-precise quantum sensors for environmental monitoring pollution, resource management, optimizing complex renewable energy grids, and for the really fundamental science, fundamental physics and cosmology, using quantum computers to simulate quantum field theories, particle physics, maybe even gain insights into quantum gravity, the nature of space-time, the universe's basic laws, things utterly impossible, classically. And then you get into even more speculative but fascinating areas. People are exploring quantum consciousness research, though that's very controversial. Space exploration, GPS-independent navigation for deep space missions, maybe new forms of communication, and even quantum biology understanding if quantum effects play a real role in things like photosynthesis or how enzymes work.
It's just mind-boggling potential across the board. And it makes sense why it's become such a global race. You mentioned the investment. How are nations and the big tech companies positioning themselves? What are the dynamics here?
Yeah, it's absolutely a geopolitical race alongside the technological one. You see huge national initiatives. China has reportedly committed around $15 billion, which is massive. The U.S. has its National Quantum Initiative proposing around $2.7 billion in federal funding. The EU has its Quantum Flagship Program, investing about $1 billion.
So governments see this as strategically vital.
Hugely. For economic competitiveness, national security, scientific leadership. And the big tech players have distinct strategies. IBM is very focused on building the hardware and providing cloud access. Google has often focused on demonstrating quantum supremacy on specific tasks. Microsoft is strong on the software and cloud platform side, partnering with hardware makers. Amazon, through AWS Bracket, provides cloud access to various quantum hardware types.
And the private investment.
It's significant, about $1.9 billion globally in 2024, and it's also very concentrated. Reportedly, just 2 big hardware companies soaked up about half of that funding. It reflects how incredibly capital-intensive building this hardware is
A high-stakes game.
very high stakes. And it raises other issues too, like the fragility of specialized quantum supply chains, manufacturing challenges, and national security concerns about relying on other countries for critical components.
So bringing this all together as we wrap up, it really does feel like 2025 is this pivotal moment. We're clearly moving from just theory towards practical reality, but wow, the engineering challenges that remain are just enormous. It seems the message is the revolution is coming, but it's going to unfold gradually, not like flipping a switch overnight.
That's exactly the right takeaway. Gradual transformation, which means organizations, even individuals interested in tech, need to start preparing now. Develop some quantum literacy, understand the basics, what it's good for, what it's not. Start evaluating potential applications relevant to your field or business. And, as we stressed, absolutely prioritize implementing quantum-safe security measures. That's not optional anymore.
Balance the optimism with realism.
Precisely. The long-term potential is inspiring, truly transformative for science and computation, but it's going to take decades, not years, for the full impact to be felt. And the initial impact might be narrower than some of the wildest hype suggests. We need patience and persistence.
Right. And so maybe the final thought for you, our listener, to mull over is this. Quantum computing isn't just about faster chips or new technology. It feels like something more fundamental. It really embodies this ongoing human quest to understand the deepest laws of nature and then figure out how to harness those laws to solve our biggest challenges. Its realization, though, depends entirely on our collective commitment to rigorous science, to relentless innovation, and maybe most critically, to developing this incredibly powerful technology responsibly.